A Chinese warship has seized a U.S. Navy underwater drone. Now, we know the unmanned vessel was collecting information off the coast of the Philippines. A Pentagon spokesperson says the incident happened yesterday, some 50 miles northwest of Subic Bay. That is near the contested waters of the South China Sea.
The U.S. Navy has been quietly assembling a new kind of fleet. Autonomous submarines that can map the seafloor, patrol for months without surfacing, and make decisions in complete darkness. But during one seemingly routine test, one of them vanished without a trace. For hours, there was nothing. No signal, no sound, no light. When recovery crews finally pulled it up, the footage inside told a story no one expected. Inside the Navy's drone revolution. Beneath the surface of the world's oceans, a quiet transformation is unfolding. The United States Navy is building a new kind of fleet, machines that don't need air, rest, or a crew. They can think for themselves, glide for months without surfacing, and go where no human vessel could safely reach. They are the Navy's underwater drones, part of a growing network of robotic submarines that are finally leaving laboratories and entering open water. At the center of this new generation stands Orca, a massive, uncrewed underwater vehicle built by Boeing and based on an earlier testbed known as Echo Voyager. Orca is enormous, close to the length of a city bus, when fully assembled, stretching about 85 feet from bow to stern. Its defining feature is the midsection, a 34-foot modular bay that can carry around 8 tons of payload. That bay isn't fixed in design. It's built like a removable trunk, allowing crews on shore to swap in different mission kits depending on the assignment. The Navy's first plan for Orca is to quietly lay mines across targeted areas of the ocean floor. But that is only the beginning. The same internal bay can hold sensors for deep sea mapping, advanced surveillance gear, and more. One hull, countless possibilities. The road to creating such a machine, however, has not been smooth. The Government Accountability Office revealed that costs climbed by more than 60% above the original estimate, and the timeline slipped by at least 3 years. What began as a plan to deliver 5 operational vehicles quickly turned into a battle against the realities of developing a first-of-its-kind submarine. Still, deliveries have begun, and Orca is now moving from Boeing's hands into Navy testing. For the Navy, the setbacks are worth enduring because Orca offers something priceless: endurance. Its hybrid propulsion system allows it to cruise silently on battery power, then recharge with a diesel generator when it nears the surface. That balance of stealth and stamina lets it stay on station for months, covering thousands of miles without a support ship. In practical terms, it means an unseen presence that can patrol coastlines or gather intelligence far from home, all without endangering a single crew member. While Orca focuses on power and endurance, another design takes the opposite approach. Manta Ray, developed by Northrop Grumman for DARPA, the Pentagon's advanced research arm. Where Orca is massive and muscular, Manta Ray is graceful and efficient, built to move like the creature that inspired its name. It recently completed full-scale testing off the coast of Southern California, proving it can operate for long periods while using almost no energy. Manta Ray glides through the water by adjusting its buoyancy, rising and sinking like a living organism, rather than forcing its way forward with heavy propulsion. When needed, small propellers provide bursts of speed. When not, the vehicle can even rest on the seafloor, going into a kind of hibernation to conserve power until the next mission phase begins. During testing, it was shipped in modular sections, assembled on the beach, and launched directly into the ocean. That field assembly concept means It doesn't waste fuel reaching its destination. It begins work exactly where it's needed. DARPA has already confirmed that parts of this design are being evaluated for Navy use, signaling that Manta Ray is more than an experiment. It's a blueprint for how the Navy can build underwater drones that last not for hours, but for months. A third design completes this trio: the Yellow Moray, a torpedo-sized underwater drone that can be launched directly from a submarine. Unlike Orca or Manta Ray, which rely on surface support, Yellow Moray fits inside a standard torpedo tube, letting submarines deploy and recover it without special gear or divers. In the spring of 2025, the fast attack submarine USS Delaware achieved a historic milestone when it launched a Yellow Moray from one of its torpedo tubes, sent it on multiple long missions, and successfully recovered it, all while deployed overseas. The Navy confirmed that this test took place not in home waters, but in Europe during an active patrol. That single event, called the first ever forward deployed submarine torpedo tube launch and recovery, proved that these small drones could become everyday tools for submariners. A crew could send a robotic scout ahead through a narrow passage, survey a harbor, or inspect the seafloor, all without exposing their own vessel. Together, these three machines, Orca, Manta Ray, and Yellow Moray, paint the clearest picture yet of the Navy's underwater future. Much of this development happens around Naval Base Ventura County in California, using the Point Mugu Sea Range that stretches toward the Channel Islands. During major exercises, locals often notice more Navy ships offshore, marking how busy these waters have become as unmanned programs expand. The work isn't without risk. In early summer of 2025, a test near Ventura showed just how unpredictable these systems can be. During one trial, an unmanned surface craft being towed suddenly activated its autonomous mode and capsized a small support vessel. Thankfully, no one was killed, but the Navy immediately halted operations and investigated the event before continuing. Understanding how difficult it is to test these machines means understanding how they actually survive underwater. Communication, navigation, and recovery, none of it works underwater the way it does on land. Underwater, radio signals simply die. Wi-Fi, radar, and even simple radio calls can't pass through seawater. Instead, drones communicate through sound, using slow, low-frequency acoustic signals that can travel only a few miles. Even under perfect conditions, a connection might hold between half a mile and 3 miles, sending only a few thousand bits of information per second. Enough for commands, not for live video. That's why most drones record everything on internal drives and send back short updates until they surface. Once they poke an antenna above the waves, they can switch to satellite or radio for faster uploads. Navigation is just as tricky. GPS signals don't reach below the waves, so each drone must keep track of its own movements with an inertial navigation system, a cluster of gyroscopes and accelerometers that measure direction and speed. But no system is perfect. Tiny errors accumulate over time, so the vehicle's sense of its position can drift by about 1 nautical mile every hour, unless corrected. To stay accurate, the drones periodically surface for a GPS fix, listen for underwater beacons, or use sonar devices called Doppler velocity logs to measure their speed against the seafloor. When it's time to return, each drone uses an acoustic pinger, a simple underwater beacon that emits a distinct tone. Recovery teams on nearby ships use hydrophones to follow that sound, triangulating the location until they find the vehicle. Many beacons are designed to activate automatically if the main power fails, ensuring rescuers can still track the signal. Those 3 systems, sound for communication, internal sensors for navigation, and pingers for recovery, are what make underwater autonomy possible. Now that we know what these machines are and where they're tested, let's talk about what happens when one of them disappears without warning. When Navy drones go missing. Sometimes an underwater drone simply stops responding. It follows its route, sending short bursts of data through sound, and then the sea goes quiet. In the deep, silence is normal, but when it lasts too long, it becomes dangerous. A lost signal might mean a drained battery, a frozen program, a snag on old fishing line, or a glider that entered the wrong current and drifted off course. Engineers plan for every one of those risks. But when contact fails completely, a routine mission can turn into a high-stakes search. And to see just how fast that silence can become serious, it helps to look at the real incidents that made the world pay attention. In December of 2016, a U.S. Navy ship called USNS Bowditch was conducting a routine ocean survey in the South China Sea. It carried a small underwater glider, a slow, unarmed drone designed to study water conditions. Unlike torpedo-shaped drones that swim with propellers, gliders move by shifting their buoyancy. They rise and sink gently through the water, using stubby wings to convert that motion into a forward glide. It's a quiet, patient way to study the ocean's temperature, currents, and salinity, and it's used by scientists and navies all over the world. On that day, the Bowditch's crew was preparing to retrieve their glider. It surfaced on schedule, about 50 nautical miles northwest of Subic Bay in the Philippines, around 57.5 miles, and began sending a homing signal. But before the crew could reach it, a Chinese naval vessel closed in and, without warning, pulled the drone from the water. The Bowditch crew watched as their equipment was carried off. The U.S. government called it an unlawful seizure and demanded its immediate return. China held it briefly, then handed it back a few days later. That's one kind of disappearance. The other happens when the ocean itself takes over. In early 2024, a 7-meter autonomous underwater vehicle named RAN went missing beneath Antarctic ice. RAN belonged to the University of Gothenburg's team, led by Professor Anna Wolin. The mission was part of a research program aboard the South Korean icebreaker Arayon, exploring how warm currents were melting the underside of glaciers. RAN had already made historic dives in the same region years earlier, mapping one of the world's most remote and fragile areas. But on the final dive of this expedition, it failed to return. It didn't appear at its rendezvous point. It didn't answer locator pings. Search crews began scanning with acoustic receivers and helicopter sweeps, trying to hear anything at all. Nothing came back. After days of effort, they had to accept what everyone on board feared. The batteries had likely drained, and the robot was gone. Under Antarctic ice, losing a vehicle isn't rare. The ceiling above is solid, meaning the robot can't surface for a GPS fix. It must rely entirely on dead reckoning and sound to find its way back. Dead reckoning means guessing your location by keeping track of how far and in what direction you've traveled since the last time you knew exactly where you were. Every sonar ping burns energy, and strong undercurrents can push it off course. If the machine misses its pre-cut hole or drifts under a ridge of rough ice, it's trapped. The design has fail-safes, redundant beacons, strict time limits, and emergency aborts. But once power fades, the silence is final. But not every disappearance ends in loss. Off the coast of Southern California, a very different story played out. During a test run near 90 feet of depth, a Navy-class Remus 600, a 600-meter rated autonomous vehicle used by navies and research groups worldwide, got caught in an old line on the seafloor. A nearby commercial dive and robotics crew noticed the problem and responded. They deployed a small remotely operated vehicle, or ROV, equipped with a camera, a claw, and a hydraulic cutter. Guided by live video, the ROV followed the tether down to the trapped drone, found the fouling line, snipped it, and brought the robot and debris back up. Each of these events, the South China Sea seizure, the Antarctic loss, and the California recovery, reveals a piece of the larger story. Underwater drones don't just vanish into the unknown. They follow rules, physics, and probabilities. And when they go missing, crews follow a strict, time-tested playbook to bring them home. The first step is always listening. Most underwater drones carry a pinger, a tiny beacon that helps crews track them by sound when they go quiet. When you hear it clearly, the boat begins to trace patterns, tightening circles or figure eights to pinpoint the source. It's slow, patient work, but it narrows the search area dramatically. If the mission was planned with extra precision, crews would have placed a few small beacons on the seafloor beforehand. The vehicle communicates with them, and by measuring how long it takes for the sound to travel back and forth, operators can triangulate the drone's position. This is called long baseline tracking because the beacons are spread far apart, hundreds or even thousands of feet, to increase accuracy. When there isn't time to deploy those seafloor beacons, a ship can use its own sensors in a faster system called Ultra-Short Baseline, or USBL. A cluster of receivers mounted under the boat listens for the pinger and estimates direction and distance. It's less exact in deep water, but faster to set up. And in emergencies, speed matters more than perfection. Once the sound leads you close enough, the next phase begins: seeing. Search teams drop a towed side-scan sonar, a long metal instrument shaped like a fish that sends out fan-shaped pulses of sound. As those pulses bounce off the sea floor, the sonar builds an image of what lies below. Objects appear as bright streaks, with dark shadows behind them. A well-trained sonar operator can recognize the shape of a vehicle, a net, or even an anchor line in those patterns. Using side-scan sonar, searchers map the area in neat parallel lines, like mowing a lawn underwater, until the missing vehicle's outline appears. Once that happens, they mark the coordinates and prepare for the final step: touching. That's where the ROV comes in. A small tethered robot with lights, cameras, and manipulator arms descends to the seafloor. Its pilot watches through live video, steering with joysticks and guiding it toward the target. The tether carries power and signal, so the ROV can stay down as long as needed. If the missing drone is entangled, the ROV's cutter can free it. If it's upright and intact, the robot can grab a handle or attach a soft sling for hoisting. This combination, pinger, sonar, ROV, is how most missing drones are recovered. Under ice or in cluttered water, the methods adapt. In polar operations, teams sometimes attach a homing beacon to the ROV itself, letting it follow the drone's signal through narrow ice tunnels. Once a vehicle is back on deck, the work isn't over. What it recorded is just as valuable as the machine itself. The data drives, whether memory cards or solid-state storage, are treated like evidence. Each is labeled, sealed, and logged before anyone opens a file. Analysts then download the data following strict national procedures to preserve timestamps, sensor readings, and metadata. This discipline ensures that what the vehicle saw can be trusted. And over time, those recovered recordings have exposed things on the seafloor that are far more unsettling than anyone expected. Disturbing footage from the deep. In April of 2023, a team from Scripps Institution of Oceanography sent high-definition cameras across part of the old dump corridors in the San Pedro Channel. The footage was supposed to be a routine verification after a mapping run. Instead, the lenses showed lines of shapes that looked too deliberate to be random. When the researchers zoomed in, the gray silhouettes on sonar turned into clear metal cylinders and steel boxes. These weren't lost tools or barrels of scrap. They were World War II-era munitions. Some were anti-submarine depth charges, heavy steel canisters once packed with explosives. Others were smoke floats, small devices ships used to throw overboard to lay a drifting cloud of smoke for cover. The pieces sat in long, curved tracks across the bottom, as if they had been pushed off a ship in a steady rhythm. One frame after another, the pattern repeated. Follow a debris line, and sooner or later, another weapon appeared. The Navy's public statement didn't deny it. Officials explained that many of these weapons were likely dumped in the 1940s, when sea disposal was considered acceptable. Returning warships simply released unused ordnance on their way home. But that short dive was only the surface of something far bigger. 2 years earlier, in 2021, the same stretch of seabed had been mapped in detail by autonomous underwater vehicles towing side-scan sonar. Across roughly 36,000 acres, about 56 square miles, the robots detected more than 27,000 objects shaped like barrels with high confidence, plus well over 100,000 other pieces of debris. The surveys reached depths near 3,000 feet. Imagine a city-sized plane where every few yards another steel drum or crate lies half buried in silt. That is what the sonar revealed, and it explained why the later camera passes kept stumbling onto dangerous relics. The munitions were disturbing enough, but the cameras caught something else, something stranger. Around many of the barrels, the seafloor looked dusted with chalk. Each drum sat in a pale ring, a white halo glowing faintly under the lights. At first, researchers thought it might be camera glare or disturbed sediment, but it was too consistent. The halos were real. For years, scientists suspected they might be linked to DDT, the banned pesticide known to linger in marine life around Southern California. DDT contamination in nearby mud and animal tissue was already documented, but no one had ever tied those ghostly rings directly to what lay inside the barrels. In 2025, Scripps scientists returned to the site with new sampling gear. They matched barrels that showed halos with others that didn't, then pulled up cores of sediment from right beside them. The lab results were shocking. The pH, the measure of acidity or alkalinity, was around 12 near the haloed barrels. That number sits on the far end of the scale, the opposite of acidic. And it means the mud there is strong enough to burn skin like bleach left too long on your hands. In that kind of environment, almost nothing microscopic can live. The sediment becomes sterile. Chemical analysis revealed why. Leaks from the barrels were reacting with magnesium in seawater to form brucite, a mineral also known as magnesium hydroxide. As that crust slowly dissolved, it released more alkaline material, pushing the surrounding mud back toward that same extreme pH and creating additional white deposits of calcium carbonate. The halos were not stains. They were active chemical scars marking where highly caustic waste had seeped into the seafloor. That discovery widened the story far beyond DDT. The pesticide is still a serious pollutant in this region, but those halos proved that many barrels were filled with something else entirely. Powerful chemical waste from refineries and factories. This kind of waste doesn't just poison animals. It changes the chemistry of the ocean floor itself. It can make metals like zinc or aluminum dissolve into mobile forms that travel with currents and accumulate in living tissue. The white rings captured were the first visible signs of that hidden process. To understand where all this is happening, you have to picture a deep section of the San Pedro Channel known as Dump Site 2. It lies roughly halfway between the Palos Verdes Peninsula and Santa Catalina Island, about 12 miles from the mainland and 8 miles seaward of the already contaminated Palos Verdes shelf. Dump Site 2 is only one of more than a dozen deep-water dumping grounds scattered along the Southern California Bight, the wide arc of coast stretching from north of the Channel Islands down past the Mexican border. Some sites took industrial waste, others received surplus military hardware. Records trace the practice back to the 1930s and show it continuing in various forms until the early 1970s, when international laws finally banned ocean dumping of this kind. The cameras also told another truth about this coastline. The seafloor doesn't separate old from new. In one frame, a World War II canister rests in the silt. In the next, a tangle of modern fishing line or electrical cable crosses the scene. Decades of industry, fishing, and shipping have layered generations of debris together, and California is not alone. Around the world, improved cameras and longer-lasting underwater robots are uncovering forgotten chapters of history. In early 2025, a French Navy training dive in the Mediterranean accidentally discovered a 16th-century merchant ship more than a mile and a half down, over 2,500 meters beneath the surface. The wreck carried stacks of ceramic jugs and iron bars perfectly preserved by the cold, high-pressure water. Seeing what's down there was one thing. Deciding what to do about it. That's where things get complicated. The Navy's next move. After the 2023 survey, the Navy said it was now reviewing everything and figuring out the best path forward to make sure the risk to people and the environment is managed the right way. If you leave hazardous materials on the seafloor, they continue to leak. If you try to move it, you might set off something worse. Either way, someone has to decide what's safer, to touch it or to leave it alone. The Navy and its partners follow a clear playbook whenever old weapons or toxic barrels show up underwater. They treat it as two separate dangers. One is the blast risk, what happens if a bomb is disturbed. The other is the environmental risk, what the ocean absorbs if that object starts to corrode or leak. In deep water, far from boats and swimmers, the chance of someone triggering a blast is tiny. That means most of the time, the safer move is to leave the object in place and just monitor it. But in shallower water, especially if the weapon looks unstable, they take the opposite approach. Plan a careful detonation or lift it out. The Defense Department even funds full research programs just to study those trade-offs. They're called SERDP and ESTCP, and their job is to test exactly when a buried bomb can be left under watch, when it's safer to blow it in place, and when it's too risky not to remove it. Every site is different. Depth matters. Currents matter. What the mud is made of matters. And now, in Southern California, there's one more factor: chemistry. Some of those barrels sitting on the bottom have leaked so much alkaline material that the mud around them burns like bleach. It's toxic even to microbes. If anyone disturbs those white halo patches the wrong way, that high pH material could spread into clean areas. That's why every move now has to be backed by data, not gut feelings. The Navy isn't doing this alone. The Environmental Protection Agency and the National Oceanic and Atmospheric Administration are both working alongside it on the Catalina Dump Corridor. They're building one shared map of what's down there and what parts are most dangerous for people and sea life. Los Angeles County has been kept in the loop, and the EPA even has a public website tracking every update about Dump Site 2. That kind of teamwork means whatever the Navy decides has to fit into a bigger plan. One with paperwork, clear roles, and eyes from outside the military watching. It also means smaller steps can move ahead right now. They can tighten the no-go zones, add sensors, and keep surveying while the long-term cleanup decisions take shape. Now, zoom out a bit. The same drones that filmed all this aren't just one-off machines. They're part of a growing fleet the Navy wants to use every year. Congress has already penciled it into the budget. Starting in fiscal year 2026, the Navy will get one new extra-large underwater vehicle every year through fiscal year 2029. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.